So what are typical requirements for the electrical power system? As with anything, as with any subsystem, you can start with size, weight, and power. You can also look at an orbit's average and peak power on the power distribution, and this will affect the wire harnessing and the motherboard and daughter board control. You can look at a specific amount of power generated and or stored. This affects the way you size the solar array and battery size. You can look at voltage conversion and limits between different components. You can also look at current regulation or limits. So these interfaces between components, that'll affect your circuit board design. For the Artemis CubeSat kit, these are very basic and general requirements, but we were looking into the CubeSat power system generating power in LEO, providing sufficient power to all other bus components. Very preliminary requirement. Here's a requirement specifying an actual number. So a minimum of 2.5 watts to charge the battery. This one's general power distribution shall supply sufficient power to all the other subsystems. And then we had an energy storage requirement that the battery shall have a capacity of at least 10 watt hours. So we drew these requirements from the documentation, but it's not comprehensive. So for your power system definition and requirement definition specifically, I want to walk through these different reference documents so that you can make your subsystem much more comprehensive. These are the documents that impose requirements onto our power subsystem. You saw from the last slide that I didn't include a lot of these requirements into the CubeSat kit, so I want you, for Thursday, to sweep through these reference documents and put these into your requirements template. Anything you find relevant from your mission, which should be mostly all of these. I realize that everyone pretty much just copy-pastes the Artemis CubeSat kit requirements, but don't assume that we got everything. I think it's clear that we didn't. I realize that we are your only exposure, so just keep this in mind as you get exposed to more sources. So let's get exposed to the Launch Services Program Level Dispenser and CubeSat Requirements document. The next few slides are going to be kind of dry, but I just want to read over the bolded requirements. So this NASA document specifies that to prevent CubeSats from activating any powered function, the CubeSat power system shall be at a power off state from the time of delivery to the launch vehicle through on-orbit deployment. This is a requirement as to the state. It doesn't say how you need to implement it, just that that needs to be the result. The CubeSat shall have at a minimum one deployment switch, which is actuated while integrated in the dispenser. The CubeSat shall include a remove before flight pin, which cuts all power to the satellite once it is inserted into the satellite. CubeSat shall incorporate battery circuit protection for charging and discharging to avoid unbalanced cell conditions. The CubeSat shall have at least 3 independent RF inhibits to prohibit inadvertent RF transmission. RF is radio frequency. And then the CubeSat shall have at least 3 independent inhibits to prohibit the inadvertent release of any deployable structures, such as antennas or solar panels. And then there was a question here, has there ever been a time where all 3 switches have failed? And I'm not sure about that. I'm not sure about all the times that CubeSats have failed. Is there a contingency plan in case this ever happens? So yeah, the 3 pins are supposed to add redundancy in case that first pin fails, then the second pin, then the third pin. That's a triple fault redundancy. So that in itself is the contingency plan. I'm assuming the backup switches, the risk of failure is minimum. It is indeed a minimum, but what happens if it all fails? Well, If the CubeSat powers on inside of the deployer because of because all of the pins fail, because all of the inhibits fail, I guess the CubeSat battery would drain. At the worst, which is what the launch provider wants to prevent, the CubeSat could cause damage to the other satellites in the deployer, which is not good. But I haven't ever heard of this happening. I'm not sure if it has. Okay. Next document. Electrical requirements from the NanoRex interface definition document. Let's go through some of these. Some of them will be redundant with the NASA launch provider, but as we know with requirements, there can be multiple that overlap. The one that you want to take is the most conservative one that applies to your system. Okay, so all electrical power storage devices shall be internal to the CubeSat. Got to be self-contained. To minimize hazard potential, the CubeSat shall not operate any system, including RF transmitter, deployment mechanisms, or otherwise energize the main power system, for a minimum of 30 minutes after deployment. So this 30 minutes after deployment happens when the P-pod deployer launches the CubeSat out with the spring. And so from that exit until 30 minutes after that exit, that's when the CubeSat can start to power on and start to do its like RF and deployment things. Another requirement, the CubeSat electrical system design shall incorporate a minimum of 3 independent inhibit switches actuated by physical deployment switches. So yeah, this one is repeated, and it goes further to say by physical deployment switches. Next one, the CubeSat electrical system design shall not permit the ground charge circuit to energize the satellite system's load. Next one, the CubeSat shall have a remove before flight feature or an apply before flight feature that keeps the satellite in an unpowered state throughout the ground handling and integration process. Next, the RBF or ABF feature shall preclude any power from any source operating any satellite functions, with the exception of pre-integration battery charging. So a little comment about this. Our inhibit switches are on the rails of the CubeSat structure. When it's inside the P-pod deployer, the switch is pressed down into the satellite. When the satellite leaves the P-pod deployer, that switch can come back out because it's not flush against the rail of the P-pod deployer. And that's what the physical deployment switch is referring to, that when it's in the P-pod deployer, the switch is physically down, and when it exits, the switch, switches to on, and that's when the electrical power system can start energizing different components. Okay, the next requirement, there shall be no electrical or data interfaces between the CubeSat and the P-pod deployer. Yeah, so there is no RF communication, there's no plugging in connectors. The CubeSat is just a disparate body from the deployer. Next, all cells and batteries on the CubeSat shall adhere to the design and testing requirements for spacecraft flight on board or near the ISS as derived from the NASA requirement document, crewed space vehicle batteries and safety requirements. We will get to that document. So this is just a little annoying because they're referring to yet another document that we have to adhere to. So it opens up a new can of worms. So question, what happens if the timer goes off later than expected? Is there a chance that the communication window is missed? It's not a big deal if the timer goes off later than expected. It is a big deal if it never goes off, if the switch never energizes the system. So essentially the spacecraft never powers on and is just a hunk of metal flying through space. Is there a chance that the communication window is missed? I mean, sure, if the timer goes off later and you miss a ground pass, that is a little sad, but given the altitude and the orbit that we're in, the next ground pass is most likely going to be within 45 minutes, so it's not that sad. Yeah, for example, Neutron 1, it's not exactly clear if it turned on after 30 minutes, but it's not that big of a deal if it comes within. I'm not going to say a general broad statement because it can be that some missions are very time strict, but for Neutron 1, for example, it wasn't like that impactful on our mission operations. Okay, next. Battery types. There is a limitation on what kind of batteries you can use. The limitation is that some batteries are not practical to make safe. For example, lithium sulfur dioxide cells have built-in overpressure vents that release sulfur dioxide gas that are highly toxic. So these, for example, that is unacceptable in the habitable area of a space vehicle. You would not want to put that inside the ISS. Other battery requirements. All flight cells and battery packs shall be subjected to an approved set of acceptance screening tests to ensure the cells are able to perform in the required load and environment without leakage or failure. Next, protection circuitry and safety features shall be implemented at the cell level to prevent an internal short circuit. Application of all cells shall be reviewed by nanoracks, and then charger circuit and protection circuit schematics shall be reviewed and evaluated for required fault tolerance. So this could be a design driver that you have fault tolerance in your circuit protection and charging circuit. For external shorts, protection circuitry and safety features shall be implemented at the cell level to prevent an external short circuit. Circuit interrupters that are rated well below the battery's peak current source capability shall be installed in the battery power circuit. In battery designs greater than 50 volts at DC, corona-induced short circuits shall be prevented. And this is referring to the solar flares or coronal mass injections, anything to do with space weather. Those short circuits should be designed to be prevented for. Overvoltage and undervoltage protection. Protection circuitry and safety features shall be implemented at cell level to prevent overvoltage or undervoltage conditions of the cell. This can come as an algorithm and a circuit. You're measuring the state of charge of your cell, and you're shunting power if the cell has enough voltage and you don't want to overcharge it. Batteries don't like to be undercharged, so there's another protection of if you're drawing power from the battery, you don't want to draw too low, so you stop operations if your battery is below a threshold voltage. Next requirement, it should be verified that the battery charging equipment, if not the dedicated charger, has at least 2 levels of control that prevent it from causing a hazardous condition on the battery being charged. For battery energy density, for battery designs greater than 80 watt-hours, energy employing high specific energy cells require additional assessment by nanoracks due to potential hazard in the event of single cell or cell-to-cell thermal runaway. Thermal runaway kind of insinuates something like an explosion happening or a battery fire happening. So nanoracks wants to make sure it's not going to happen. Lithium polymer cells or pouch cells shall be restrained at all times to prevent inadvertent swelling during storage, cycling, and low pressure or vacuum environments, with pressure restraints on the wide faces of the cells to prevent damage due to pouch expansion. For button cells, these batteries shall be clearly identified by part number and UL listed or equivalent. Almost done with this talk. Finally, capacitors used as energy storage devices are treated and reviewed like batteries. Part number and electrolyte must be identified, along with details of how the capacitor is used and any associated schematics. All spacecraft components shall be electrically bonded per SSP 30245 to ensure the spacecraft is free from electrical shock and static discharge hazards. Okay, so many requirements. Walk through them, see which ones will apply to your subsystem. And then last 2 slides on requirements. So remember the Johnson Space Center crewed space battle, this document. It was referenced in NanoRacks. Let's walk through it. The pertinent parts talk about qualification testing and acceptance testing. So these are the tests you have to do when it comes to batteries. Qualification testing shall be performed to the worst case relevant flight environments with margin. Environmental tests shall include at minimum extreme temperature exposures, vacuum, and vibration tests. Charge and discharge cycles or a load test at 20 degrees Fahrenheit above and below worst case hot and worst case cold. After that, you do a functional baseline check after doing these environmental checks. Then you expose it to vacuum, do a leak check, then you do a functional baseline test recheck. For batteries used in a pressurized volume or environment, exposure to a vacuum for a minimum of 6 hours should be carried out. There's a flight cell, so the battery cells you actually want to use for flight. Those you need to do destructive testing for a randomly selected sample. Then the operation of cell safety devices shall be verified by a qualification test at the battery level or at a level that accurately simulates the level at which the control is required to confirm the operation of a safety device. And then to verify cell manufacturing quality does not vary within the lot, you do that destructive testing. Qualification testing shall be performed at the battery level using flight equivalent builds. For acceptance testing, so this is after you do qualification testing for functionality. These are for the real deal, what you're going to install on the spacecraft. You have to do 100% acceptance screening. That includes visual inspection, measure the mass, the OCV retention, it pertains to outgassing, and then AC and DC resistance to make sure that internal functionality is still working. Then you have to do flight acceptance non-destructive testing for those same things, a functional baseline test, vibration test, another functional test, vacuum, then another functional test. So you can see that space really cares about batteries. They can be quite dangerous, and that's why there's so much documentation and constraints on the way that we handle batteries. Okay, let's go to a little bit more exciting stuff. So other requirements in the process is the selection of different metals in the construction of your boards. So tin whiskers are known to develop in space, where you see here that here's a terminal, it has some voltage running across it. After some time, if this were pure tin or zinc, these whiskers can form and short between these two terminals, which is very bad. Not like you can go into space and fix that. So what you can do is prevent these from forming by not using pure tin or zinc terminals, connectors, solder. In the development process, you want to make sure that you manufacture your electronics on an electrostatic discharge mat in ESD safe ways. So you see this person is wearing a wrist strap. The reason why we do this is because if there is just a tiny amount of electrostatic buildup on your hands, on like paper, and it touches the component, these tiny little components can short and have permanent damage to them. In that way, it can incapacitate this component, this board. In other ways, it can mess up, just like the board can still power up, but it doesn't function quite like it used to. So why is that? And it can be because a component is damaged, but the overall board isn't. So sometimes you waste a lot of time by having this component damaged, and then you have to debug, and it turns out that because of bad electrostatic discharge hygiene, this component broke and you have to replace it. So like, just blanket statement, when you're working with electronics, try to be in an electrostatic discharge safe environment. Have good practices when working with these components because they are sensitive, and you don't want to waste time or break components, which is wasting money. Yeah, so paper is not good. It's an insulator. It can build up charge. Like there can be two pieces of paper that build up charge, and when you hold them close together, they'll hug each other, right? You don't want that charge crossing some like air boundary and then hitting the board itself, or just like physically making contact and creating a short. Okay, and then some other requirements. So say you have a spacecraft that is built and you need to deliver it. How do you even deliver a spacecraft? A lot of people hand carry them, and so they need to take flights on airplanes and then need to follow TSA guidelines. So because of that, because we hand carry spacecraft, for the CubeSat kit, for example, we have lithium-ion batteries, so we're limited to 100 watt-hours or less per battery. So yeah, those are kind of just like the peripheral requirements that we accumulate in the process of making spacecraft in the whole life cycle. So a little bit more about tin whiskers. Yes, there was a question that we don't really know the exact reason for their growth, but the reason why is because there are many different factors and we can't really say the exact cause. So we can say, excuse me, there's plating chemistry, plating process, deposit characteristics, substrate, environment that affects the creation of these tin whiskers. And we can do our best to mitigate all of these different causes, but there's not an exact cause and effect of totally eliminating tin whiskers. So yeah, you can see here the different failure modes that tin whiskers can create: electrical shorts, contamination, metal vapor arc. Here are some different shapes and features of tin whiskers. They can look like these nodules, kinks, filaments, solids, rings. But these are the ways that we mitigate tin whiskers. Reduce stress on metal plating. And here are some ways to do that. Use physical barriers to insulate. There's something called conformal coating, which is like after you have a final design of a circuit board, you take some coating material, some soft coating material, and then layer that entire electrical surface so that none of the conductive surfaces are exposed to the environment. It's good practice, but if you can conformal coat before it's finalized, like you want to make a change on the surface of the board, you can't do it anymore because it's coated with this layer of stuff. And then minimizing stress through handling, assembly, and application. Avoid pure tin or zinc if possible. So yeah, I think I addressed all of these questions. So let's zip through design considerations, process, and drivers. There is a design process, and I'll just walk through each step. So at the very beginning, you want to define the power consumption and electrical characteristics of the spacecraft bus and components. Here's an initial budget for the way that you should distribute power in your spacecraft bus. The payload is what should really drive. So the payload should typically take between 40% to 80% of your spacecraft. Your attitude control, if you have actuators that take up a lot of power, 15%, comms, 5%, command and data handling, 5%, and on and on. Power takes up quite a bit, and structures, pretty much nothing. You can size your overall power system by saying that if you want to target 40% for your payload, and you know your payload takes up, say, 40 watts, then your overall power system needs to be rated for 100 total watts. Yep, so that was just the step that I went through. Yeah, so that's a good initial distribution. Next, you select your power generation and energy storage methods, and then you analyze the system's power budget and profile from the beginning of the mission to the end of the mission to ensure the selected components are sufficient to supply power. This is a snapshot of Artemis CubeSat kit's power budget and profile. So you can see here that we looked at an orbit. We looked at the amount of power generated from our solar panels. We also looked at the amount of power consumed per mode over the time that it takes to go through that mode. And you just want to make sure that the amount of power generated and the amount of power consumed over some period of time, in this case an orbit, balances out, that you can recharge to the level you were at the beginning of that cycle. Yeah, so once you are confident that the components, your system architecture, can balance power, then you can start to think about the nitty-gritty details of designing a power conversion and management system that handles all of the interfacing between the power sources and power consumers. Here is a PCB board, a design of this is the payload board. So you can see there are a lot of different components that handle that interface. Yeah, and then I'll ask Amber Amaihong, an avionics engineer in our lab, to walk through how to make these kind of schematic diagrams. But this is later on in the process. This time around, we'll just be worried about up to this step, the power budget step. All right, later on in the process, we procure, buy, and fabricate components. Here are batteries. Here is an EPS board, electrical power system board. Here are some students who are working on the integration and assembly of the various boards. And you can see these little wires coming off that connect to the boards. Then we conduct tests. Here are the batteries in a thermal vacuum chamber inside a hazard-safe bag. And to review, here is the procedure of how to design, fabricate, integrate the electrical power system. Okay, and then here was a question about the attitude control system, how there's a high percent allocation for average power. And so there is a comment about Wikipedia saying to use permanent magnets for the magnetorquer. And wouldn't that save on constant power drain? So yeah, it would save on constant power drain if you have a passive magnet that is orienting your spacecraft. But then the trade is that permanent magnets cannot vary the directionality or magnitude of their field. So you would be stuck with a single static configuration. You would always have to have your permanent magnet aligned with the magnetic field direction around the Earth or whatever body you're orbiting. So that's why there are active magnetorquers and, let's say, 3-axis control, so that you can vary in all three axes your orientation. This gives you flexibility and also pointing precision, which permanent magnets, can't offer. Okay, I think I'm done with lecture today, so I will stop recording.